Next part, we're going to the math. Okay, this is gonna get intense. So we know that J theta is an expectation, all right? An expectation over continuous variables can be written in an integral as an integral. So this is the distribution over which we are taking expectation, right? And this reward is just a scalar. It's the thing that we care, we want to maximize. And it's taking the integral over the trajectory, tau. All right, so we want to do gradient, right? We want to pass the gradient back to the parameter theta. So we need to take the gradient over this objective. So let's take the gradient. Then it looks something like this. But this is trouble because we only have samples. We only have samples of the trajectory. If it remains these forms, then we cannot evaluate the gradient numerically. So which means we need some transformation in math. So here's a convenient identity, which you probably seen this before in some textbook something. All right. So you take the logarithm of a distribution and multiply it with the distribution itself and take the gradient. It equals to the gradient of the distribution itself. And we just plug it into this equation, right? We substitute this gradient part with this quantity here. So we get this part here. And this is good because now we can express this equation as an expectation, right? We take this pi theta of tau and this d tau and the integral out. Then it becomes back to the expectation. But the gradient operator still here, which means we have access to some way to evaluate the gradient. Okay, so now we can evaluate the gradient, which means we can update the parameters of our policy. Okay, this is good. We need to convert. So the whole thing in this page is to convert the gradient into an expectation so that we can estimate it with the samples we have, which are trajectories. But this is not enough, okay? Because if we remember the joint probability of the trajectory, this pi theta tau, here is still trouble. Right, now let's go into the next step. So now we want to deal with this p theta tau here. Remember that p theta tau is a joint distribution of the initial distribution, the policy distribution, and the transition probability distribution. So because we are taking gradient, right? We are taking gradient. So if it's a joint distribution and we're taking gradient over them, it's gonna be hard to compute. This is the reason why we take the logarithm of this pi theta tau, right? Because the multiply operator after the logarithm will become a addition, okay? So this multiply here, they all become addition. And we need to notice that the gradient of the parameters theta over the initial distribution and the transition distribution are just zero because they are not depend on the policy parameters. The only thing that depends on the policy parameter is the policy itself. Which means if we plug in this log pi theta tau into this gradient equation, we can cancel out the first term and the last term, which we only have the policy remain, right? This is why we need to take the logarithm. Okay, now this is our final equation. The gradient of our objective will equal to the expectation over p theta tau of a sum over the log probability of the policy distribution and times the reward return. And this is great because this is what we actually have. Because in most reinforced learning problems, we don't assume that we know the transition distribution. For example, for a robotic manipulation task, it's impossible to get the exact distribution of the transition probability. Okay, so what's left is what we can estimate with samples. So take a look at this equation. The log probability of the policy distribution. This is something we can compute. And this is always something we can compute. Okay, we just take sample, compute the thing, multiply them together, backplot into the policy network. So this is all the math that we need to know about the reinforced algorithm. Okay, so I write it into a estimate with samples. So it's an approximation. We approximate this quantity with samples, right? We can approximate the objective with a samples of rewards. I is the index of sample. T is the index of time step within each trajectory. And similarly, now we can estimate the gradient of the objective of the parameter theta. Okay, it's approximated by samples. We take n samples, denoted each of which denoted by I, and we get a bunch of pi theta probability, and we take the logarithm of them, we multiply it with a return, then we get a gradient that we want. So this is the reinforced algorithm. So it composed of 3 steps. First one is sample a bunch of trajectories from the current policy. So just run a policy on the environment, and then we estimate the gradient. We backpropagate it with some learning rate alpha to the parameters. This is the reinforced algorithm. Okay, so now let's look at the form, and we can compare it with the maximum likelihood algorithm. So this is the policy gradient we had before. And the maximum likelihood looks like this. This is something that often used in supervised learning, where you get a bunch of a data set of data of input and output, which you are going to assume that this data are good data. So for example, in an imitation learning task, you get a human to provide a bunch of demonstrations. So it composed of a bunch of states and actions that provided by the human that we think are good actions. And then we just fit those actions with maximum likelihood. We just match their probability, their log probability. Okay. So this is the equation with maximum likelihood, and we look at it. And when we look at them, we notice that the only difference is this term. The RL, the policy gradient algorithm, have an extra term, which is the return. So we can think of policy gradient as a weighted version of the maximum likelihood. And why we want to have this, and why we want to have this weighted, have this returned, it's because we are not having good actions in a reinforced learning paradigm. Okay, the agent is exploring the world randomly. So the only way to measure the goodness or the badness of the actions are the value of the returns. So this This simply means that if the rewards of some actions are good, then we just level up. We just level up the probability of those actions. And if the rewards are low, we think that those actions are bad. So we just lower the probability of those actions. Okay, cool. Now let's look at the implementation part. So for we can apply policy gradient with discrete actions or all continuous actions. Let's first look at discrete actions. If assuming that we are having a neural network, so if our output of our neural network is discrete, because we have discrete actions, then the final layer of the networks will be followed by a softmax activation, by which we can get a distribution. We can get a discrete distribution of the actions. A softmax activation makes the output of the network into a 0-1 distribution. Okay, so those values sum to 1. And this is similar to a multi-classification network. Okay, so if it's discrete, then we get the probability directly. And we can just take the logarithm of them and multiply it with the returns. So this is our gradient. This is cool, this is easy. But for continuous actions, it's a bit tricky. So it depends on the policy class that we choose. For example, if we choose a Gaussian policy class, a multivariate Gaussian policy class, if we look at this part, our policy is represented by some neural networks that output the mean. This is the mean, and some standard deviation. So this standard deviation here can also be output by the neural network, or it can be set to some kind of constant like 1, a 1 matrix. So if you work out the math yourself, you can get the gradient of the log probability in this form. If the standard deviation matrix is just the 1 matrix, then this is equivalent to the mean square loss it's a really common loss in machine learning. So this is the mean output by the network. This is action that we get from our samples. All right. And fortunately, if you implement it in with PyTorch will compute the gradient for us. So we don't have to write this computation code by ourselves. So here's a snippet of the code I write. Okay, so we get a network to output a mean, and we just directly output the log standard deviation here. And in training, if we want just get the actions, we can just get the actions. But when you want to update the network, we will need a log probabilities. So we can get the log probabilities computed by the PyTorch automatically, right? Which is quite convenient. So this part, the bottom part here is the update part. We get a bunch of new actions, the log probabilities corresponds to these actions. So this is how you compute the values of compute a gradient of the policy of a Gaussian policy. And after you get a gradient, you just call 0grad and backward the gradient into your policy network. Okay.